Alright, I'm Dalton, and I'm reporting on the Rankine cycle today. And the objectives for the reporter on this was to calculate the mass flow rate, the pump work in, the boiler heat input, the condenser heat removed, the turbine work produced, the turbine efficiency, and the cycle efficiency. This is the ideal Rankine cycle, which we've seen a lot. Pump goes into a boiler, goes into the turbine, which is going to produce the work, and then goes into the condenser, which will lower it back into a fluid, so it can go into the pump and do into the cycle again. This is the TS diagram for that. For the ideal case, from 4 to 1 right here is the pump, which is isentropic. From 1 to 2 is the boiler, which is isobaric. From 2 to 3 is the turbine, and you can see how if it goes, the ideal case is to go straight down and be isentropic, but for real case, it's probably not going to be that, and it's going to go to the right some. And then from 3 to 4 is the condenser, where it is also isobaric. And also, this is the ideal for the real case. You usually have to extend this out up here because you don't want it to turn into a mixture of steam and water in the turbine because that's not good for the turbine. So in reality, you have to heat it out here and then go down. Alright. This is the apparatus that we use, which had a couple more parts into it. Like it had the steam separator right there before the turbine, which gives you higher quality steam. And it also has the steam trap, which vents out some of that extra water. And these were the equations that we used, which is the work into the pump is a specific volume, which is a constant in the pump. The difference in pressure times the mass flow rate. Anyway, I won't read them all out. This is what I got for the results. This was measured from the flow meter, each mass flow rate. Get your work in from the equations earlier, and to find all these, you have to use the equations. We measured the temperature and pressure, and then from that temperature and pressure, you have to find out what state it's in, and then go to the tables in the back of the book and look up all your H values and solve it that way. It's really tedious. It wasn't very precise. I had to make some assumptions, like some of them would be like really close to the saturation curve on the TS diagram, so I would just bring them down a little bit. Let's get in this. That's all I have. Anybody got questions?
How close were your results with the other classes?
The other classes? My efficiencies came out pretty close. Some of them, I was looking at a lot of other class results for this. They were all over the place. They had some 80%, but most of them seem to be around that 15, 20, 10 range. Any other questions?
Dalton, can you go back to your slides once again? Go back to the slide where you have shown, the one before that. Great. And you mentioned that in the ideal case, you have the isentropic situation, like it directly comes from point 2 to point 3. But in the real case, it doesn't. Why do you think so? Why it doesn't?
Well, isentropic means constant entropy, which would mean it's also adiabatic, and our turbine over there is obviously out in the open, so there's going to be some heat transfer, which will make it not adiabatic.
Right. Yes. So if it is isentropic, it's reversibly here. Right? So when you assume adiabatic conditions, it means that you have no heat transfer. That's not perfectly true. That's one of the reasons. Then you have the other things also. Like you have a lot of interactions going on. It's not an ideal device. So you have some losses. Anyways, any other questions?